were serious puzzles.
Apologies, I forgot to start that until just now.
So I'm going to start. There are three unanticipated results that led to three ideas, forced us to come up with three ideas called efficiency, catch, and the conformational wave. After some thought about it, we combined the catch and efficiency ideas into a linear for energy relationship, is what's shown in that little box there. And the wave we turned into a map of energy at the transition state. And after a lot more pondering, like about 10 years worth, I'm going to combine now this linear free energy and energy map into a zipper mechanism for activation of the receptor. Now, you may not know what all this stuff is right now, but I promise you by the end of the talk, you'll know what I'm talking about. So the nicotinic acetylcholine receptor is a ligand-gated ion channel. As Marcel says, it's important in the nervous and in the immune systems. There's also many subtypes, so pharma is interested in developing subtype-specific partial agonists. But my interest, as I just said, is the nicotinic acetylcholine receptor as a model system, as a prototypical allosteric protein, or as Jean-Pierre Changeau calls it, the hydrogen atom of allosteric proteins. So just to establish its credibility as that, these are some firsts that were first identified in nicotinic acetylcholine receptors, including the idea of a receptor. And I won't go through this list, but I think just scanning it, will see there's some really fundamental things that came from our study of nicotinic receptors first identified there. And you look at that, the years, and it looks like, oh, well, this is all last century. What I'm going to try to convince you is that these ideas I'm going to talk about today, namely the wave, catch, efficiency, and the zipper, are all, they may be general and pertain to all receptors. I'm not sure about the wave and the zipper, but I'm sure about catch, and I'm very sure about efficiency. So these are the three things that I'm going to concentrate on: affinity, efficacy, and efficiency. Affinity is binding strength. Efficacy is the maximum activity that the ligand can produce. And efficiency is the correlation between affinity and efficacy, as I will go on to show you. So the extracellular domain of the muscle type receptor has two neurotransmitter binding sites that are equivalent and independent in the adult type receptor. In the fetal type receptor, they're not equivalent, but they're still independent. But we're going to be talking only about the adult type today. In the transmembrane domain, there is a gate, which is a region in the center of the pore, which can go from dry over on the left to wet on the right. And when it's dry, ions can't get through, and when it's wet, ions can get through. And this shift between wet and dry is a function of the global isomerization of the protein between two states. This simulation came from Toppin Nyack, by the way. So I saw the date of today's seminar, 2/2/22 at 2 p.m. So I decided to call these binary proteins instead of allosteric proteins. So receptors are binary proteins. They have two native states with two outputs and two input sensitivities. So this on the left here is a potential energy surface or an energy landscape showing the two native states as energy wells, points of stability. And we're going to name those C and O for closed and open channel. And C has weak binding, low affinity for ligands, and O has strong binding. So nature has made it that in the absence of agonists, O is much less stable than C, so it's an uphill reaction. So the probability of being O is very small without any ligands, about 10 to the -6 in the receptor we'll talk about. The system changes when you add agonists, and that's because the agonists of that different input sensitivities, you get a little bit of stabilization energy to C from the agonist. You get about twice as much stabilization energy to O, and that turns this uphill reaction into a downhill reaction. So to a first approximation, I mean, this is a true statement. Agonists turn on receptors because they bind more strongly to the on shape. I think this is, if you don't accept this as the rule, you're not going to believe anything I say the rest of the talk. This is how receptors work. Now, there's another state in here that's the in between C and O, which is the transition state. It's a point of instability. It's drawn as a barrier here. And you can see here that in many receptors, the transition state, and the receptor we'll talk about, the agonist provides the same energy stabilization to the transition state as it does to the open state. So the difference between the unligand and the ligand condition is manifest as an increase in the opening rate constant. You can see that this mountaintop gets much smaller when there's a ligand around, so the opening rate gets faster. The closing rate stays pretty much the same. So it's the opening rate, but we're not going to talk too much about kinetics here. We're going to talk equilibrium. So we won't talk about that. And it's these two blue lines determine affinity, efficacy, and efficiency. That's all you need to know, is that the length of these two lines. So the length of the line, it gives you the energy for C and O, and that's the log of the equilibrium constant is what gives you the energy. So that's the two energies binding to C and binding to O, weak and strong. So we can turn those energy landscapes into a thermodynamic cycle where you have unliganded condition on the left, liganded condition on the right, and weak binding on the top and strong binding on the bottom. And the word affinity usually is used by pharmacologists to go to just the weak binding, because this is the physiological activation pathway. The other pathway exists, but it's rare, but it does exist. So people like to draw a linear, just the physiological route, but there really is a full cycle here. And of course, there are two binding sites. So if we're going to try to do physiology, we'd have to add a second binding site. And receptors do other things, like, for example, they desensitize, which means go into some other state that has high affinity but a closed channel. And that would be drawn as a plane. And if there are four different desensitization states, so I'd have to draw this as a four-dimensional hypercube. And then there are modal shifts between one set of rate constant and another set of rate constant, that has to be drawn as well. So if you're going to try to do physiology, this model gets extremely complicated. But we're not trying to do physiology, we're trying to dive deep into the receptor. So in our experiments, we take care to eliminate all those extraneous events: desensitization, channel block, heterogeneity. We select those out of the data so we can get a very clean image of this. We even knock out one binding site and look at one binding site at a time. So this is not physiology, this is going into the receptor, not into the cell. So this thermodynamic cycle, in 1840s, Germain Henri Hess made an observation which turned into a law, and he said this. By the way, he was a Swiss chemist who Catherine the Great had brought to Russia to try to civilize Russia. It didn't go very well, but he came up with this sentence here, which you don't have to read because I'll summarize it. What he said was, getting across the diagonal of a thermodynamic cycle is the same whether you take the energy change is the same whether you go by the clockwise or counterclockwise pathway. By the way, this was before the conservation of energy was known. So what that leads to is this green equation that the ratio of gating constants is equal to the ratio of binding constants. And that ratio is called the coupling constant. And if I did two equal binding sites, I would have to square the coupling constant. It would be, you just have to square that term on the right. So some people have argued that it's, in order for this to be true, there has to be a closed system. There has to be no external energy coming in besides temperature. And some people have argued that in ion channels there is. So we set out to measure this, and it's possible using single channel methods to measure all four of these equilibrium constants. In fact, we can measure all 8 of the rate constants in this thermodynamic cycle, and we have done so. And when we did so, and we looked at the equilibrium constants, we found that Hess's law is valid, that for 8 different agonists at 3 different binding sites, that relationship holds. So there is no external energy coming into the system. Everything happens spontaneously, and the word spontaneously just means driven by temperature alone. Doesn't mean unliganded, it means driven by temperature alone. And that's in that paper on the lower left. So I think this is going to be true for all receptors too, if it's a starting point. It's possible there will be energy coming in some receptors, but I think as a starting point, you have to accept both those energy landscapes and the fact that there is no energy coming in. It's just everything's thermalized. So we can get these rate constants by single channels, but that's sort of esoteric. Not everybody can do that, and not all receptors are suitable for that. So the other way to get at what I want to get these equilibrium constants is from a dose response curve. So we all know a dose response curve, minimum, maximum, and a midpoint. Efficacy refers to the maximum because the minimum is the same for all agonists, and potency is a word that refers to the midpoint. But you can relate these three terms, max, min, and EC50, to all four of the equilibrium constants by these simple equations to the right. The last one, KDO, is from the green equation. And the problem is minimum is sometimes very hard to get. So later on, I'll show you how you can avoid even measuring the minimum. That if you just measure max and EC50, you can get L2 and KD, the weak binding energy. So that's the way I'm trying to encourage people to do this. And I think if you can get a dose response curve that you can fit to a Hill equation and get a maximum and a midpoint, then you can take these two and run with them. So let's do this. Here's some dose response curves for acetylcholine, a frog toxin, epibatidine, and tetramethylammonium. And we happen to know, we took about 10 years to learn, but we happen to know the E0, the minimum value, the L0, which is 7 times 10 to the minus 7th, as it turns out. Later on, I'll show you, you don't need to know this, but we just happen to know it. So I'm putting it to use. So we can measure EC50 and max from fitting these equations, fitting these data points to a Hill equation, and we get the two binding energies, the two equilibrium constants. One is in the micromolar range, one is in the nanomolar range. And if you take the ratio, you get the coupling constant, which is on the order of a few thousand, 6,000 for ACH and 1,500 for epibatidine. So that's good. We can get those two. And we've done this for about 50 different agonists. And here's one paper here where we did 13 of them. And you can see the range of the coupling constant is indeed from 6,000 all the way down to 5 here for butane. Choline, which is a breakdown product for ACH, is present at high quality in synapses, is a much smaller coupling constant. So this coupling constant translates into a maximum open probability of about 0.96, and the choline translates to about 0.05. So this is roughly from 1 to 0 is these coupling constant ranges. And on the right here, I've just taken the log of the coupling constant and expressed the U as energies. And people who like energies like us, like our lab, we talk in energies, we don't talk in numbers. We in equilibrium constants or ratios, we talk in log terms. So an antagonist is a ligand that has a coupling constant of 1, which means it doesn't do anything, doesn't provide any energy. And an inverse agonist is a ligand that has a coupling constant less than 1, and it provides positive or unfavorable energy. Now, I mentioned that we were able to measure the rate constants for all those steps of the cycle. So what I just want to show you here as an introduction to linear free energy analysis is that we make a plot of the log of the equilibrium constant versus the log of the opening rate constant versus the log of the equilibrium constant. And these give you these green lines that I'm showing up above. So the one on the right is the equilibrium constant energy change, and the one in the middle here, the one on the left is the transition state from the rate constant. And you can see that these two lines are roughly the same amplitude. The slope of these lines is the ratio of these two green lines. And you can see for all these agonists on the left, they fall on the same line. And the line has a slope of 0.95, which tells you that the transition state change. At the transition state, the energy of the ligand was approximately the same as the energy of the ligand in the open state. So at the transition state, the ligand was energetically open, which implies means structurally open too. So I just want to point out that water is on this plot. Water falls on this plot. So water is not an agonist. It's really the perfect antagonist. It's at the agonist inverse agonist divide. It defines the zero energy point. And one more thing I want to say is that if instead of changing the agonist, we had changed the ligand, the residue to which the agonist binds, and there are only a handful of them at the binding site. If we change those by making mutations and see what happens to the opening rate and the equilibrium constant, we get the same plot. We get a slope of 0.95. So both the agonist and the residues have an open-like character at the transition state. So that's the bottom sentence there. Agonists are just like removable side chains. There's nothing special about an agonist. It's just a tiny little chip of a molecule that comes in there about the same size as a residue, and it just has different stabilities and closed and open. Okay, so that's the introduction to receptors. Maybe I could stop for a question or two about this that I think applies to any receptor that opens rapidly is going to have a transition state that's stabilized by the ligand to the same extent as the open state.
I have a question for you.
I do have a question. Oh, Tom, you go first.
All right, are you sure?
Yeah.
So Tony, you made a comment about, if you don't accept kind of the MWC picture of the ligand binding more tightly to the open than the closed state, then we're not going to believe anything else you say. I'm just curious, what do you think personally about the KNF model?
I think KNF, and I think it's old fashioned to even talk about all this stuff. I mean, KNF and, I think that's an old fashioned way of thinking about things. And I also don't like MWC because I'm just talking about thermodynamic cycle. So things are happening inside of this transition. It's not instantaneous. We write C and we write O, but it's not instantaneous. So there are partial movements that I will talk about in the third part of this talk. There's a lot of wiggling going on the nanosecond or 10 nanosecond or 57 nanosecond. So there are intermediate states, whether it happens subunit wise or domain wise, I'm not sure. But there is, at the end of the day, a global switch in conformation into two stable wells. There may be lots of different bumps along the way that involve subunit by subunit transitions. But I think it's really no longer useful to even talk about MWC and KNF. I think that's sort of an old school way to talk about things. So that's my opinion. I don't know if that answers your question, but.
Okay, well, it's your opinion, so that's what
I'll
it is.
show you. I think there's a ton of stuff going on between C and O. So as anybody who does any MD simulations will tell you, I mean, there's a trillion things going on between these two stable end states. That energy diagram is a very low resolution view of what's going on.
So
Okay. Thanks.
I had a question about, so I think the acetylcholine receptor has two ligand binding sites. And when you're talking about the KD, is that referring to an apparent KD, or what's your assumptions with how to treat ligand binding to these receptors?
Yeah, we kill one binding site either by making a mutation or putting on a toxin. So we have a single receptor binding site. We measure the rate constant using single channel kinetics. We measure the rate constant for getting on and the rate constant for getting off. And we take the ratio of those two off over on to give you the KD. So this is KD for one single binding site based on kinetics of rate constant. It's a very precise, very, detailed measurement. We're not doing wholesale stuff. We're getting it from single channel currents.
Tony, just a couple of things. I really like your experiment showing that you're not getting an energy source from the ion gradient. But I was wondering, did you go further and try that with different driving forces?
No, we've only worked. Yeah, we have. We've worked it out at plus 70 and minus 100. We've done this at two different voltages. And it's true with that. We didn't do it at anything in between. Yeah. But that would be the experiment that I try to get those that were saying there was a gradient was contributing to that cycle. That's the right experiment to do. And we didn't actually do that explicitly, but we get the same answers when we do it at plus and minus.
Yeah.
So, yeah.
The other thing is that I think the one case where I think there really is an exception with that is in the CLC chloride channels, where I think they really are getting energy from the gradient in that case.
Yeah, I think you get energy from the gradient at permeation wise. When you're when you're down at the gate, and you do get energy from the gradient permeation wise. So there are substates that are asymmetric going forward and going backward in time. Yeah. But I think that's not the same as the MWC or the thermodynamic cycle. That's a different different thing that you're measuring.
Well, it operates weirdly because it's different in the closed and the open state, and it has to do with hydration of the inside of the pore and things like that.
Yeah, things are, yes. But but Rick, you once asked that when I was in Austin, you asked about voltage gated channels, and I wouldn't mind having a discussion about this maybe later. That I think that model that of the thermodynamic cycle does apply to voltage gated channels. If you say that the horizontal steps are the deposition of energy into the system, meaning voltage times charge, and the vertical steps are the isomerization of the protein, which includes the gating currents. So the movement of S4 is, and that signal that you get is not the energy coming into the system. That's the energy change associated with that step, which I will call hold. If you stay to the end of the talk, there's a similar event like that in acetylcholine receptors, but it doesn't give you any kind of a signal. So you guys have the signal. But I think that the reason why MWC, they say doesn't fit is because as you hyperpolarize, you can shut it off arbitrarily. Well, that's just the coupling constant. Voltage is just making the coupling constant arbitrarily. You can make it's an inverse agonist. You can shut off the acetylcholine receptor as much as you want by adding a difference in that energy between those two blue bars. You can make that as big as you want. So I really do think that voltage gated channels do fit into this scheme, as well as mechanical channels and everything else fits into the scheme.
Yeah,
as you can make it.
I completely agree with that. I think that it's pretty much impossible to say that there's no opening with the voltage sensors in the resting state. Anyway, it's a signal to noise issue, and if it's a big equilibrium constant, then you're not going to be able to measure it.
No, that's not even it, Rick. You can shut it down arbitrarily stuff. I think L0, the 0 point for voltage gated channels, is the equilibrium constant at 0 voltage.
Yeah, no, that's what I'm talking about.
That's quite big. You can measure that easily.
Right. Yeah, but even without the bias that gives you, I don't think you can get it down to 0. To zero PO.
Yeah, but L0 doesn't mean 0 activity. It means 0 input. It means 0 input voltage.
Right.
So you can get it as it's arbitrary. Okay.
Yeah, so I think that's a misconception that people have that say that.
I think we should have a Zoom meeting for.
Yeah, we should. It'd be a lot of fun.
To clean it up. Yeah.
Yeah.
So is that it?
Tony, I have one question.
Okay.
Claudio, here. So, have you ever tried in the LFER for different agonists? Have you guys? I left the lab 20 years ago, almost exactly today. So, have you ever tried ligands that are not quaternary ammonium cations? Epibatidine, that's epibatidine, nicotine, any organic molecule. How do they?
Nicotine definitely does. I don't know. Do we ever measure? We know the rate constants. I don't. That's yeah, we have the data. I'm not sure I've ever. That was 20 years ago. We would do that stuff, but I have all the data for that. We measure everything at the single channel level, so we have all the rate constants, so we could make that. And I'm pretty sure that the closing rate is the same for all the agonists. So the difference in the equilibrium constant is coming from the forward rate constant. I've never seen an agonist where you get a slow rate constant or a fast rate constant. Well, except for maybe a few. There's some that were like, we tried pyridine, pyrimidine, and that has a faster rate constants. So that's about 4 times faster. So there are some agonists that do this, but I think the agonists that I'm going to be talking about today are all in the forward rate constant.
Very good.
Yeah. Okay, so now we're talking about it. The next topic is efficiency, which I think is a very core property of receptors that has been hiding in plain sight for 50 or 60 years. It could have been discovered in 1967, as soon as Arthur Carlin said, and Sean Joe said that the acetylcholine receptor is an allosteric protein. Somebody could have done what I'm about to show you. So the efficiency of a machine is the Greek letter eta, is the standard thermodynamic symbol for it, is just simple energy out over energy in. So in words, that means that the agonist efficiency is the fraction of binding energy that is converted to gating energy. So that's the definition of efficiency, and it's very easy to calculate. We know from the green equation there that the energy out, which is the coupling constant, that's how much the equilibrium constant, the gating equilibrium constant changes with the addition of one agonist. That is the log of the green equation there is the numerator of this equation. And the denominator is how much energy can you get from the ligand? Well, that's just log KDO, the high affinity, the strong binding. So you just take the ratio of those two and you get the equation, the pink equation here. 1 minus the log, the energy ratio. And when we derived this, we were really excited. But in fact, this is just a standard equation from a thermodynamic cycle. I think Sadie Carnot derived this with temperature hot over temperature cold back 200 years ago. So that ratio, log KDC, log KDO, is just the ratio of those two blue lines. So now we're going to define those pharmacology terms in terms of those two blue lines. Affinity is just the length of the blue lines. There are two affinities, to C and to O. Efficacy is just the difference between the two lines. And efficiency now is the ratio of the two lines. So you have the length of the lines, the difference between the length of the lines, and the ratio of lines are determining the three core pharmacological properties. And this is why I think efficiency applies to all agonists of all receptors, because if there's two lines, then there's a ratio, and that's the efficiency. So let's go back to our dose response curves and look at it with an eye towards efficiency. You can see that ACH is more efficient than epibadidine because they're about the same on the concentration axis, but ACH gives you more. And you can see TMA is more efficient than epibadidine too, because it has roughly the same maximum output, but it requires a higher concentration coming in. So we take those numbers, we get those KDs, and now we calculate efficiencies. So ACH is 50% of the energy that binding energy gets converted to gating, 42% for epibadidine, and 54% for TMA. So those are the quantitative numbers that you can get from just max and EC50 from any dose response curve. So every agonist at every receptor has an efficiency. So if you have a dose response curve, you can calculate an efficiency and you can compare these things quantitatively. Now, you may have intuited that by inspection, but now we have a quantitative way to get that. And that's sort of interesting, but that's really not what makes efficiency interesting. I'll show you what makes efficiency interesting in a second. But first, I want to go to the next point, which was what I said was that we get rid of desensitization, we clean up our signal by getting rid of all these extraneous events. And I just want to show you, we went and did whole cell experiments. So the top panel here is from an ion flux machine where you just transfect ACH receptors into hex cells and you superfuse ACH. You have about a 200 millisecond exchange time. And you can see the dose response curves are not exactly the same between the whole cell and the single channel method but when you take the numbers and run them through the equations, you get the efficiencies and you see the relative efficiencies are about right. Now, I think desensitization is lowering the efficiency, the apparent efficiency, by about 3% for all different ones. But you can see that you can do this. So you can do this with a whole cell measurement and with any receptor. So I think this is really a general thing, this efficiency thing. And I think I encourage people to try to do this. But we're going to stick with the single channel method because it's better. It gives you a clearer picture. So this is the first surprise, the first puzzle. And this is how I felt when I saw this. When Snail JD came into my office, I asked her to plot these. We had just measured L0, so we were able to calculate KD0 with the green equation. And I said, let's plot these two things. And she plotted them, and this is what she showed me. It was a plot, a straight line with the points right on the line. It didn't matter whether you're acetylcholine with a maximum open of 0.96 and a EC50 of 40, or choline with a maximum open of 0.05. The entire range from 0 to 1, you fell on the same line. There's something, I'll go through what these agonists are. Each point is a different agonist. These agonists belong to the same tribe. There was something common about these agonists. And the reason I was so surprised is because allosteric theory never said anything about this. It just said, you got to be to the right of that dashed line. You're going to have a higher binding to 0 as you do to C. But when that's what you expect and that's what you get, there's something going on. And we didn't know at the time. That was 2012, and it was only a few years later that I learned about efficiency. But now I know what this means. It means the slope of this line is KDC, log KDC, log KDO, which means all of the agonists have the same efficiency, which is amazing. Okay, that's what that results. So this is what makes efficiency interesting. There are these agonists belong to the same class. They all have the same efficiency. So just for 1 second, I want to introduce a new plot called an efficiency plot, which is if you take the pink and green equations and you combine them, you get the blue equation. And this is just a straight line. So y equal mx plus b. If you make a plot of log binding on the x-axis and log gating on the y-axis, you get a straight line with a slope that is you can use to calculate efficiency. So here's that plot for those agonists I showed before, plus some more. So this is to the 9 different agonists and at 2 different binding sites. That's why there's so many points here. And you can see they fall in a straight line. And if you measure the slope and you calculate efficiency, you get 51%. So all of these agonists have 51% efficiency. And this is the basically log KDC is the energy into the system, and log KD is energy out. So this is an input-output curve of the energy coming into the receptor. And you can see the first point is the same N applies to different agonists of different scaffolds. So ACH has a quaternary mean, nicotine has a tertiary mean, DMPP has a quaternary mean, but it has this junk at the back end. So different scaffolds, these are choline analogs, anabasine, carbachol, nornicotine. All these guys fall on the same line. And this line pertains, as I showed you with choline and ACH, it's over a wide range of efficacy and affinity. So this axis down here is affinity, and this axis, the y-axis, is efficacy. So we did this for 20 agonists. So that was 9. Here's 10 more. So these are the epibadine. This is what epibadine looks like. We started with epibadine analogs, epiboxidine, anatoxin A, azobicycloheptene, and cytosine, which has a bridge nitrogen, but a bigger ring down here. But also tetraethylammonium and tetramethylphosphonium. It doesn't even have a nitrogen in it, fell on this red line, okay? And these 3 agonists, TMA, DMP, and DMT, fell on a different line. And I will and I will show you later on why this is definitely significant. 54%, 51 is definitely significant. So we fit all these to a straight line, and independently. We fit the green, black, and red to straight lines, and when they all projected to the same y-intercept, which is log L0, which is the same as the one that we took 10 years to measure. So if you want to measure L0, all you got to do is do a couple of agonists that have the same efficiency, and I'll give you some ideas what that means. And you can fit those and get a straight line. You can get log 0, and you can go ahead and calculate KD0 if you want, just like we had done. You can calculate all the equilibrium constants that way. But you can see here that the L classes are discrete. There's not a lot of scatter all over the place. They're really tightly aligned, and they're very precise. This 54 and 51% are different. It took us a while to understand this because, you know, we used to measure 54 or 51, we call them the same. I'm down to now 51 and 52 might be different. I think some of the scatter in here might also be different, slight differences. So that's 19 agonists. There was one that I didn't say. There's another one here, varenicline, which is a smoking cessation drug. We didn't get anything else like it. So it was an outlier. So we just used the same L0 and calculated the efficiency for that. And we're now trying to measure some more 35% agonists. That's in the pipeline. So one thing I want to point out, if you talk to a pharmacologist, they will tell you, well, there is no correlation between affinity and efficacy. People have measured it and there isn't any. And if you look at this data and you didn't know anything about efficiency, you would say these 3 agonists here all have the same affinity, but they have different efficacies. And these agonists here have the same efficacy, but they all have different affinities. So you would say, if you did those points, you would say there's no correlation. And I think only when you understand that there are efficiency classes is obvious they're hiding the correlation because there are multiple classes. If there was a large number of classes, I would agree they wouldn't show up. But because classes are discrete and limited in number, then if you get enough data, so I think people do 4 or 5 ligands and they call it quits. This is 20 ligands on 3 different binding sites. This is a ton of data. So I think it's only because we had lots of data that we could see these efficiency classes. Each point here is a complete CRC. You need a full CRC to get the efficacy and affinity. So efficiency is the correlation between affinity and efficacy. Now, what about other receptors? Well, I don't know. We didn't do these. These are taken from the literature. We found what we thought were 4 pretty good papers where they measured efficacy and affinity. And we just took their data from their tables and replotted them. And you can see that, and what we did is we did a statistical filtering of outliers. There's a standard method to get rid of outliers. So the red points were outliers and the blue points, and we fit just the blue points, and we got efficiencies in the range of 39, 59, 49, 52. If we take this, so reasonable numbers, and L zeros are on the order of 10 to minus 4th, 10 to minus 5th in here. So again, it would look like there was no activity without ligands. But in particular, I want to point out this muscarinic receptor because there's a lot of stuff going on after the receptor conformational change. But it's the same for all agonists, and it probably just represents an offset to the efficiency. So you can do this for GPCRs. You can measure GPCR efficiency from a dose response curve. And number 2, in this paper, they said these 2 points right here are a clear example of how there is no correlation between affinity and efficacy. They make a point of saying this in their paper. I would do this. I would say there's another class. This is octreotramine and pilocarpine. These are big molecules. These are small molecules like acetylcholine, carbachol, methacol, bethacol. So these are a different structural class, and I'll get into that in a few slides. So I think if they had done a lot more of these ring compounds, that they might have seen more points around here. They did 6 and they were happy. They needed to do 20. These guys did single channel measurement. This was a very good paper from Trevor Smart's lab. So these 2 guys happen to have sulfur in them. They were the only 2 ligands that have sulfur. So again, this may represent another class, although I don't know. My point is you got to get a lot of data.
Tony, to what extent could you look at the molecular structures and hypothesize what a class will be and then test it this way?
Yeah.
See if they fall on the right line. Okay, great.
Next slide.
Thanks.
Right. By the way, Rick, the calcium turns out to be about 60% efficient. If you just take the what's their name? Sweet and what's the name of that paper? I'm blocking on the name of the paper, where they have KDC, KDO, where they measure the 2. If you just take log KDC, log KDO, 1 minus that, turns out to be about 60% for that. Yeah. But I don't know what other ions are. I'm not sure if that's ever been measured for strontium or any of the other divalent cations or something like that. But
we may have a little bit of data, probably not as wide a range, but yeah, we should talk about that.
I think anybody who has I think it should be measured at every receptor binding site. That's my opinion. I think it's a very fundamental thing to know. But as far as structure goes, we just make this plot, which is the efficiency as a function of the ligand head group size. And it's a little hard to define the ligand head group size. We just took the chemical structure and took 1 bond away from the nitrogen. But I think there's rotors, and I think you have to do MD simulations to get a really good estimate of that ligand volume. But we just did a very simple rough one. And it looks like there's a correlation, an inverse correlation, that the bigger the ligand, the smaller the size. Although something complicated, many other things might be going on, but ligand size seems to be one determinant of efficiency. That needs to be explored, but that's what our first blush, that's what it looks like. So let's look at the binding site. Now, the next few things are going to be more very specific to the acetylcholine receptor. This is what the binding site looks like. It has a cluster of 5 aromatic residue side chains that form a pyramid around this nitrogen. This is the key nitrogen right here in the middle. And this is surrounded by these five. This is from Ryan Hibbs's lab. And there's also a glycine up here that I'm going to talk about up in this loop, this loop here. And I'll also mention this loop here, which is called loop C. That'll come up in a little bit. So we did MD simulations of homology models and of subsequently of crystal structures. And what we find is that the pocket is smaller in O. So those five aromatics contract between C and O, but they all start out about the same. So with the independent of agonists, we did ACH and epibadidine here. You can see that the closed volume is about the same, but the open volume is smaller in ACH. So the extent of contraction is more with ACH than it is with epibadidine. So this is the summary of that for 4 different ligands at 2 different binding sites, and 4 different ligands at just the alpha delta site here for epibadidine. So this is epibadidine, epiboxidine, antitoxin, and azobicyclohexane. Each bar is a different agonist. And you can see that they do start out about the same. In our homology model, this came from a real structure, but the extent of contraction is about twice as much in ACH than it is in epibadidine. So contraction is less with low efficiency ligands. Is that clear? I hope that's clear. So our hypothesis is that contraction is limited by van der Waals contacts with the agonist, and so the binding site tries to contract, but it can't when you have a big fat agonist in there. And when it contracts less, you get less energy transferred into the gating machinery. This needs to be tested. This can be tested through simulations by calculations of energy and separation of energy into van der Waals, electrostatic, Poisson-Boltzmann, et cetera. So that's something we would like to do. But we think that's our working hypothesis, that there is a pocket contraction, and that seems to be a robust finding. At the extent of contraction is correlated with low efficiency ligands, and that needs to be extended into more ligands than just what we studied. The other thing we did is we made mutations of the aromatic residues. This is 44 different mutations. And for each one of these, we had to measure E0 to get this number. So this is a lot of work. And most of the mutations didn't do anything. This is ACH efficiency. Most of the mutations, the efficiency stayed at 51%. But a few of them, it shifted it up to the 55% level, including all mutations of this W149. Big fat tryptophan in there. When you get rid of the tryptophan, the efficiency went all the way up to 60%. So efficiency can be increased, and it also can be decreased. Only one residue here, Y190A, dropped the efficiency down to 35%, which you remember is the same as varenicline. And you remember this is the same as TMA. We're talking about ACH here, which is 51. And we also made 16 different mutant receptor agonist combinations of G153 of that glycine, including the S mutation, which causes congenital myasthenic syndrome. These are all high efficiency agonists. They dropped them all down to 42%. So it didn't matter whether it was 51 or 54, they all went to 42%, which you remember that's what epibadidine was. And there is one over here, this nicotine on G153K was down to 32%. So based on these, about 100 different, there was about 80 different combinations here. We say that they look that the N values, the efficiencies are not only discrete and precise, as I showed you in that efficiency plot, but they're modal. So I think this is like a spectrum or maybe a barcode. I don't know which is a better analogy, that this is giving you a line spectrum of that binding site, that you have 54, 51, 42, and 30. That's how the binding site shakes out. That's our, so our hypothesis is that binding sites, when they can only adopt a discrete number of O structures and those structures correlate with efficiency. So the binding site's not a rubber room It's not induced fit. They call it conformational selection, but it just means that the binding site can tries to get to structure A, but if it can't get there, it goes to structure B. And if it can't get there, it goes to structure C. There's only a discrete number of target structures that the binding site can go to in the O conformation. So structural biologists, that needs to be solved by using structural biology, but that's what the electrophysiology is telling us here. So let's get back to general stuff. That was all ACH receptor stuff. This is that blue equation. And if you know the slope and the intercept, then you can calculate one from the other. So you can calculate max from EC50, and you can calculate EC50 from max. You say, well, what's good of that? Well, it's because these two things, efficiency and L0, are, I think, very base features that you want to know your receptor. So if you have a receptor, you want to know L0. And if you have an agonist, you want to know the efficiency. So L0 applies to all agonists. So all you got to do is make one of those plots, measure L0 from the intercept, and then you're done. You can go ahead and scan 1 billion compounds, and it's always the same L0. So you just measure it once, and you never have to measure it again unless you make a mutation. But for each, or change the receptor, but for each receptor, you have one L0, and it applies to all agonists. So sooner or later, you're going to learn L0 for your receptor. And second of all, efficiency applies to agonist cap and can be predicted from structure. That goes to your equation, Rick. If you have nicotine here, which is in a 51% efficiency, you can add an R group onto here, but it only is dependent, I think, on this moiety, the head group volume. So you can change the efficacy and the affinity by zillions by adding whatever you want over here. It will make a huge difference, but I think the efficiency will stay the same. So you probably, for a whole class of ligands, you can have a pretty good idea of what the efficiency is going to be just from the structure. So I think someday you'll be able to know efficiency from structure, but right now you'd have to measure it. I would agree with that. So that's your question, Rick. Can you get efficiency from structure? I think someday, yes, but right now it's a little bit early days. But so what's the good of this? Well, the good is you can take a dose response curve. These are the whole cell currents now. And you can just take the maximum response and calculate an entire curve from just one response. Because you know from max, you can calculate EC50, and therefore you can calculate the entire thing. And similarly, if you have a normalized dose response curve, a lot of pharmacologists normalize them because they don't know how many channels are contributing to the response. So you take a normalized, and if you just take EC50 from those, you can take EC50 and you can calculate the entire curve. So you can calculate efficiency, you can calculate efficacy if you know efficiency. Okay, is that clear? That you know that you can take this curve, this gray curve here, and blow it up into this curve and know the absolute max for these things if you know, just from the EC50, if you know the efficiency in L0. So the EC50 can be estimated from the response to just one agonist concentration. You go to some really high agonist concentration, you measure the response. If you know L0 and efficiency, you can calculate the full dose response curve from just one. You don't have to scan a bunch of concentrations. And here you can, efficacy information can be recovered from a normalized concentration response curve. Now this curve on the right shows that we used efficiency, two different efficiencies for the TMA. If you take a 50% efficiency, you get this lower green curve, which is a terrible fit. But if you bump it's very sensitive to the efficiency. So if you bump the efficiency, you use to 55%, you get quite a good fit. In fact, this is probably a good way to estimate efficiency. If you take this curve here, and if you have this curve here and you normalize it and you ask, what's it take to turn this curve into this curve, you can probably get efficiency that way. That's something that I would like to work on. I think you can get efficiency just by doing that. So,
but this will be affected by desensitization, right?
Not much.
Your ability to get the curves to say what you want will be affected by how much desensitization goes into the dose response curves.
Yeah, probably, except that the efficiency you measure probably factors that in. When you use that number of efficiency, that's probably factored in.
Because it's a ratio.
Because yeah, it lowers the efficiency of all the agonists there. So I don't think that's gonna, yeah, it might.
Yeah, I'm not saying you can't do something about it.
Yeah, I think, and also the L0 is not that sensitive. We've gone through a perturbation of L0. You can go 10 to minus fifth, 10 to minus sixth, 10, you get roughly the same answer. So you're going to roughly get a dose response curve from a single point, I think. And so let me finish the efficiency part of this, which is efficiency is general. Anytime if you have a system that you think behaves according to this energy landscapes, you're going to get an efficiency. It's the ratio of those two lines. In ACH receptors, there's classes. That's what makes efficiency interesting. If every agonist had a unique efficiency, it would just be all over the place. And efficiency, I agree, would not be that interesting. What makes it interesting is that there are discrete classes, and that there are modes, although this needs to be proved in more detail. There's a spectrum is what you get when you do efficiency. It's also useful, as I just described, in terms of dose response analysis, and it's accessible. All you need is EC50 and max. You don't need a whole lot to get this. Anybody can get this. Is what I mean. It's been hiding in plain sight for 50 years. Anybody could have gotten this, and it's also informative, which means that's the next part of the talk. So this was going to be my break point here. So is anybody left listening? I don't know. Is any questions about?
Yeah, we're all still here.
I'm going to leave efficiency behind. No, I'm not going to
Hey,
leave it
Tony?
behind. I'm going to go into more biophysics and energy now.
Tony, can I ask a question? It's Cindy.
Yeah, I Cindy.
Hi. So do you think, because of these different classes in efficiency, do you think, or have you tested any, say, allosteric drug modulators in the presence of an agonist? Does it change the class? The
No,
efficiency? Would a drug binding, say, somewhere
Yeah.
else in the, a PMA for
That
nicotinic acetylcholine receptor, would something like that, do you think, change the efficiency or change the class?
Okay, that's a good question. It might. I mean, I view the efficiency means there's going to be a long range propagation back to the binding site of transfer of energy, because you're changing either KDC or KDO.
Right.
So if you put a modulator that binds in the membrane domain, it can either change L0, that's a local event, that you can change just the local energetics of the protein going from left to right.
Mhm.
And that's just an L0 effect. And that's my guess is how most allosteric modulators work. There may be some, I'll show you a slide at the end that says there's not many things that change long distance that we have found. I think that may be a backbone event, but it may be there is a drug that can change efficiency. And I don't know, that should be looked at. It's the efficiency of the machine is a sort of a fundamental property of it. And it may be that drugs change the efficiency. I mean, I want to just mention here that the congenital myasthenic mutant lowered the efficiency from 51% to 42%. And that may be the core cause of the disease, that you're lowering the efficiency at which the machine is working. But in terms of allosteric modulators, there's someone in Oxford who's trying to see if that's true. But yeah, that's something to look at. But we haven't found anything that did that yet.
Okay.
I think along the same lines too is that, to what extent do you know whether mutations away from the binding site can cause class changes for a particular group of agonists?
Yeah, well, we're moving that direction. We have moved, we would like to do that, and we've moved a little bit away. And there are some mutations, maybe 20 angstroms away, that we have found to influence efficiency, and they seem to switch classes. So they move.
That's really cool.
They move the black guys into the red group, and these are not at the binding site. These are a little bit further away. I'll tell you, they're K145 and D200. Cindy knows what these are, and Claudio knows what they are. But they don't change.
So Tony, so all you need is something that constrains the compression at the at the open site, basically in order to get a different class. And that doesn't need to be local.
Yes, yeah,
Right.
my hypothesis is that it's a balloon that collapses and there are springs that attach this balloon to the rest of the protein. So when you get this, or a bicycle pump, whatever you want to call it, when the thing collapses, it pulls on springs and that moves energy out into the rest of the world. And if you change those spring constants by changing something else, you will change the efficiency of the machine. But whether it's modal, it goes into one class or another, we don't know that yet. So far, the early data looks like it does move classes, mainly down in the 42 and 30. This 30% class is a little bit spread out. We get 28, 29, 35, 32. So we're trying to get enough data so this shows up as a discrete Gaussian. But we get the 51s going down into either 30 or to 41s, except this guy here, the green guy stays almost the same. So we don't quite understand what's going on, but yes, but it would be nice to find something far away, like in a transmembrane domain or at the domain interface or something that would change efficiency.
Mhm.
That would be fascinating, because that means there's a long distance propagation from that site back to the collapse of this pocket, and we haven't found that yet.
The other thing that I thought was cool, and it kind of requires thinking about this in a slightly different way, is that you showed us data showing that the mean distances within the binding pocket were changing, but the shapes of the distributions were too. And it could be that the bigger effect is not so much the shift in the mean, but the narrowing of the distributions that you see in your MD calculations.
That's possible. That's possible. We didn't look into that. I mean, we're having a discussion now. How do you measure volume? Everybody likes this programs called Whole, where you actually put a water probe in there and find the volume. And I don't like that, because you're measuring all kind of junk outside the pocket. I like this bottom here, bottom right, you make a pyramid and look right in there and you get a nice higher resolution of that. But whether it's the variance in that as opposed to the mean, it could be. Yeah, that could be. I guess that's entropy or something like that.
Yeah, it might be interesting at some point.
Yeah, that's a good idea. But I'm going to launch now. We're out of time. So I'm going to keep going. If that's all right.
Yeah,
Marcel?
please do.
Okay. So now I'm going to talk about the zipper. This is the idea that I've been pondering for 20 years. So let's see where this goes. So we're going to start with the second surprising result, which is that the association rate constant into C is slower than into O and agonist dependent. This came from those experiments where we measured these things individually that I showed you very at the beginning, each of the thermodynamic cycle, but also some work Claudio did way back in 2001 that shows that getting into the open channel is faster than getting into the closed channel, and getting into the closed channel is different, and it's correlated with potency. And this line is diffusion, 4 times 10 to the minus 9th. It's an estimate of diffusion. So the reason she's upset is because she thinks agonists diffuse into the binding site. If you look into textbooks, you read papers, or we talk to people, they say, well, the agonist diffuses into its target site. Well, these 4 compounds all have the same diffusion constant. They're not going to diffuse any differently. And number one, they would say that there's loop C closes over the binding site. It's called capping. And that this closure of the loop over the binding site that the structural biologists see in between an empty site or a site with an agonist, and the stronger the agonist, the more the closing they see. It's a clear result from the structural biology world. And they say, well, that must prevent agonists from getting in. That's the reason for high affinity, is what the thought is. But that, therefore, the agonist would get in more slowly to O than to C. So this is what people expected to see. And this is what we recorded in that paper in 2017. Again, for 4 different agonists at 3 different binding sites, a very robust finding. So what is going on? Okay, that's the question. And as an introduction to this, I want to just talk about intermediate states. So our idea is that the slow on rate is due to a conformational change that's required to get the agonist into C. There's a rearrangement that has to take place to get it into C. And I'll talk about the O being faster in a second too. So I'm going to introduce these intermediate states by starting with Michaelis Menten, who stuck an ES state in the reaction and revolutionized enzyme kinetics. And it took 30 years later, but Britain and the invention of the, until Britton Chance invented the stop flow apparatus and got a signal and said, yes, there is an ES state. 30 years it took. 1955, Del Castillo and Katz, Del Castillo was my postdoc advisor, took this activation scheme and put an AC state in there in order to account for efficacy. And again, 30 years later, the invention of the patch clamp by Nair and Sockman, Cahoon and Sockman find that state. So it's 30 years between when the kinetics guys imagine the state and when the technical guys find the state. Okay, and of course, the structural guys are another 20 years behind these guys. So I don't even know so the AC state still has not been found, but I'm sure there's ES states been found. So we can break apart each of these states. So we can break apart this state, the AC to ACO, the green arrow. And I did this in 1992. This is how I got my tenure, was on this paper. And I found this state. I called it I labeled it as AC prime. This is a figure from the paper, and I called it stepwise. I gave it a bad name. People told me not to give it that name. I did it anyhow. And that's a state between AC and AO. And again, in 2011, this was rediscovered by David Cahoon and Steve Sine. They gave it the much more sexier names, flip and primed. And it's the same state, but they did a much better job. It's much clearer. It's about a 5 microsecond state. I barely could see it back then in 1992. So there's a lot of stuff going on in here, and that's going to be the final part of the talk. I'll talk about that in more detail. But right now, what I want to do is break apart the binding step. As I said, there's a conformational change required in order to get the agonist into the pocket. So in binding, there's 2 steps. There's diffusion, and then there's this conformational change. And the only part of this conformational change is the agonist dependent part of this change is KD, I'm going to still call it KDC, is this blue bar right here. So for all agonists, the diffusion component's the same, but KDC is what's different for different agonists. And similarly in gating, there's the L2, the agonist dependent part of L2 comes from things that happen at the beginning of the gating isomerization, and the rest of this isomerization is going to be the same for all agonists. That's I'll develop that idea. So I'm going to call this rearrangement catch. That's the one that it's a local rearrangement of the binding site that lets the agonist in and leads to weak binding. And this conformational change is the pocket contraction I talked about. That's the coupling constant. That's what switches it to strong binding site. So this is the coupling constant. Hold is the coupling constant, and catch is KD. Other things happen to contribute to those equilibrium constants. Here, these equilibrium constants, but they are not agonist dependent. They represent constant offset. So every agonist, there's an offset here that comes from diffusion, and every agonist, there's an offset here that comes from isomerization of the protein, the rest away from the binding site. But this plot, the slope of this plot is not affected by that. Is everybody clear on that? That's what catch and hold is, because I'm going to use those 2 words. Catch is the blue bar, and L2 is the L bar. Okay. And AC prime, that intermediate state, stepwise flip prime, is this gray stuff happening in here, somewhere in this gray stuff in here. We'll get into that later. So what do I mean by a local rearrangement lets the agonist in? Now I'm going to try to match this up with the capping idea from the structural biologists. So the idea is that the ligand's far away, it diffuses up to the site to form this complex called A-C, A-C, and then the catch conformational happens. Loop C caps, some pathway opens, the agonist enters, and you get weak binding. So loop C, the capping of loop C is not a steric boundary. It is something that opens a pathway or is consequent to the opening of the pathway. I don't know which happens first. And then the agonist that allows the agonist to get in. So capping doesn't prevent the agonist to get in, it allows the agonist to get in, or that. And I can talk about some data that we have that's consistent with that. And hold, the pocket contracts and you get strong binding. So this is what these are cartoons. I don't know what the structural are. If I was a structural biologist, I would tell structural biologists there are 1, 2, 3, 4 different structures you need to find at the binding site. Forget about the intermediate states and gating right now, but if you're interested in the binding site, you need to know the apo site, this site, the actually low affinity site, and the AO site. And I don't think any of those, maybe AO has been found. I don't think even AC hasn't been found. It's been found with bungarotoxin bound, but not with an agonist, because these are transient. These guys last hardly at all, nanoseconds, microseconds. So this explains also this weird idea that O binds fast, because in hold, the pocket contracts, but this opening that you have made in catch is still available here. So you can still get in there at diffusion. You can diffuse in now because it's already happened. This pathway has been established in catch. So if you find yourself in the open state without an agonist, then we can do that easily by making mutations. Then that's how we measure this. That's how you can get in rapidly. So that's my cartoon way of thinking about how you can rationalize capping and fast binding to O and slow binding to C. And it's this equilibrium constant. This is the key thing to understand. This little patch, wherever this patch is, and we don't know where it is, the binding of ligand to here, which triggers catch, which is the first step in catch, is the essentially key event in the activation of the receptor. So I think this is very important, this to understand where this site is, and that's something we would like to look into. But I think I won't. I think I'll move on, because I could talk for an hour about this slide. But so let's go back to the catch and hold as an energy landscape. So this is the energy landscape just for catch and hold. So this is energy and this is binding site structure. And you can see these lines. These are the two blue lines. This is binding to C. This is the catch conformational change. And this is the hold conformational change, which is the coupling constant, which we know this is the energy for that. So the sum of these two is just KDO. If you add this and this, you get KDO. And the idea here is that these two rearrangements are tethered by a linear free energy relationship. So whatever happens to catch happens to hold. They happen together. This whole landscape tilts up and down. So if you have a weak agonist, you get the same ratio of the blue lines. So the magnitude of the blue lines change, but the ratio of the blue line stays constant, which means that the efficiency stays constant. So this is why choline and ACH can both fall in the same family, because their energy changes are correlated, which means somehow that their structures, it probably means their structures are correlated. Whatever rearrangement happens in catch is also going to happen in hold, probably. Although I've talked to some people, protein chemists, who tell me that's not necessarily true. You can have correlated energies without correlated structures. So I don't know that yet. But this is linear free energy is what tethers catch and hold, and that crosses the binding gating divide. So catch is in the binding side of the equation here, and gate and hold is in the gating side. Remember, that's the green and gray of the gating side is where hold is taking place. And what different efficiency agonists do is they move this midpoint around left and right. That's what a high efficiency agonist moves it this way. So a greater fraction of the energy is in hold. So let's go through just to be clear what I'm trying to say here. And this is this is the energy landscape before the agonist arrives, and now it's arrived at that black patch and formed this this A-C state. And what that does, it lowers the transition state for the catch rearrangement. So I've drawn a funky transition state here so that catch can take place. That event lowers the transition state for the hold. Whatever the structural change in that rearrangement is, it probably resembles the transition state for the collapse of the binding pocket. And that is that structural match between the transition state and the previous state lowers the energy, and so that the hold event can take place. Other things happen. So this is where the idea of a zipper came from. So this is the binding gating crosstalk that gives you efficiency. That's the reason there's efficiency. So this is why I call it a zipper. And I'm willing to change the idea of this word zipper if people don't like it. Some people have told me that's a bad idea. So the idea of a zipper is that the formation of this clasp, the bottom clasp here across the clasp, lowers the transition state of that one to this condition. So that's that cycle there. And then you get the next clasp that forms, which is the next energy well. And that lowers the transition state of that clasp to be that. And then so on and so on. So what a zipper is doing is it's sequentially lowering transition states. It's a bunch of linked linear free energy relationships is the idea that I have for a zipper. And maybe I didn't say that very clearly, so maybe we can talk about that when I get to the end. I'm trying to get to the end here. So this is that energy landscape shown as a state model. Some people prefer state models. So this is the main activation pathway. You diffuse, you catch, and you hold. The thickness of the arrow has to do with the equilibrium constant. You rarely hold without catch because you need catch to lower that transition state. So catch promotes hold by lowering the transition state. But if we go back to this guy's Germain-Henri-Hess, then if these two arrows have to equal the sum of these two arrows, which means if this is small, this one has to be big. So hold promotes catch. So if you find yourself here in the lower left-hand corner, you're going to catch pretty quickly. This is a huge equilibrium constant in order to satisfy microscopic reversibility of this cycle down below here. So it goes backwards. Microscopic reversibility insists it goes backwards, and that's going to be important in the channel closing process. So let's talk. Okay, so should I wait for a question here, or should I just keep pushing on? There's one more section. Is anybody there? Am I done?
We should go ahead.
Keep going. Oh, I'm sorry.
Okay. Is there a question? No, okay, I'll keep going, right? Is anybody there? I can't hear anything.
Yeah, no, it's great. Keep going, please.
Okay, so that's the zipper idea. So let's go to the third puzzling result, which is the result that that took me took about 10 years worth of data in here, which is about 1,000 mutations, which is that slide I showed way in the beginning of the opening rate constant versus the gating equilibrium constant log that gave this idea that gave the two different green lines for the transition state and the end state. Well, we did that for lots of different mutations of residues all over the protein. This is about 1,000 mutations are in this plot for maybe, I don't know, 30 residues or 50 residues. I don't know, 100 residues, I would say, maybe more. A lot of different residues all over the protein, mostly in the alpha subunit. And what we found is this 1, 2, 3, 5 peaks. There's clearly 5 peaks, although the last peak at the 0 is not very well defined, but there looks like to be 5 peaks. And these are the slopes of those lines. So at the transition state, the green guys were about the same as the open state. The red guys were 80%, 60%, 33%, and 6%, like that of the open state. So what does this mean? This is a puzzle because before we did this, I think people would have thought that would have been the result. Either they're like the open state or they're like the closed state. But no, this is the result. This is a lot of labor in here by a lot of different people. I'll show you their names at the end. It started by Claudio. Well, what this means is there's a cascade of gaining rearrangements. So we worked out a theory, both from simulation and math, which I'm not very good at, but I had help from Yu Zhu and Srirupa Chakraborty, that if you have this is not drawn very well, is it? If you have a series of conformational changes that are in a sequence, if you perturb, let's say, this first one here and hold, if you make a mutation that stabilizes this energy with the rest of them being the same, you're going to end up with this phi value, which is the slope of that line of being close to 1. And if you perturb things in the middle, you'll get a 5 value in the middle. And if you perturb the very end of the reaction, you're going to get a 5 value of 0. So this is the, I hope you can see that these wavy lines have been offset from the green bars, from the bars underneath them. So each of these peaks represents a domain rearrangement in the protein, or an energy change. If you want to think of structure, it's a domain rearrangement. If you want to think of energy, it's a change in this landscape, the energy landscape here, that occurs somewhere in the structure. And this is the green and the gray area that I showed you before. This is the agonist dependent one. So all these green guys are at the agonist binding site, and these guys are in the well, I'll show you that in a second. So this is the theory that says phi is related to sequence. So that's what these 5 peaks means, that there are 5 sub events in there, and I gave them names because stepwise didn't work. So based on flip being so successful and being useless, if you ask me, that it's hold, twist, tilt, rip, and pop is what I'm calling these. Just to see if you could, just to try to get somebody to pay attention. Nobody pays attention to this. This data has been around for 10, 20 years, and it's completely ignored. And I think that this phi analysis is really the right way to look at a transition state. If you want to find direct events with flip, you're going to go crazy, because these events only last about 100 nanoseconds and you just can't see them. So the final result I want to show you is this is mutant cycle analysis. We had about 80 different pairs of mutants. So we measured the effect of mutation A and mutation B, and then the pair of them together, and measured how much the pair deviated from the sum of the individual mutations. So if they're additive, then that means those 2 side chains are not, those 2 mutations did not interact. So the dashed line represents KT, which is thermal background noise, and the vast majority of these points, even when they're close together, this is the C alpha distance between the mutations, they don't interact. So side chains are not interacting with other side chains, and the ones that do interact are mostly 15 angstroms within each other. There's a few out here that don't, and I don't know what to make of these. But this pink line really represents our noise that we can, that's 2 KT. And I don't think we can get better than 2 KT in our measurement, maybe even more than that. But you can see the ones that are far away are close together, anything further than 15 angstroms away. So what that says that this sequence of events, this hold, twist, tilt, rip, pop, can be associated with discrete structures. So hold is only things in the green circle gave you the green phi values. The red circle gave you the red ones. The yellow circle was the yellow histogram. Orange is around, circum the gate, 12, 13 prime near the gate. And the blue ones were right at the gate, 9 prime, right at the gate. And so we think that that's why I gave these names. Hold is the contraction of the binding site. And in structures, there seems to be a small twist here. It's also a contraction of this binding site, is what twist is. Tilt means there's 4 transmembrane helices, and they change their angles in the tilt reaction. Rip is these residues near the gate pull apart, and we think pop is water, is when water actually joins that fusion of water at the tip, is what causes an energy reaction. So phi not only gives you sequence, and it gives you location. It doesn't give you time. The value of flip, which is this whole thing together, everything you see here combines to give you flip. These 4 states here together form flip. And it's about 5 microseconds. So if and when we get a device that can give you 50 nanosecond or 10 nanosecond resolution, my prediction is you will see 4 flips, not just one thing smeared together. So that gives the idea of a conformational wave, combining the idea that phi gives you sequence and the mutant cycle analysis gives you structure. You can combine those, so this is our idea of a conformational wave. That's the opening series of events, and this is the closing series of events. Okay, has everybody got that? One more time. That's opening, and closing is the reverse because of that Hess, the microscopic reversibility.
So, Tony, can I ask a question? Tell me if this is, we should wait on this question, but now that you're getting down to quick times compared to what we can resolve experimentally, have you thought about what would happen to this interpretation if you used a different formulation of the rate equation, like a Cramer's approximation or something?
Yeah, I don't think it matters. I mean, Cramer's, I don't know. Cramer's is so hard. I never understood.
Yeah.
that. I mean, I
Well,
tried to read that paper.
it's weird because it has friction, which I don't know what is at the microscopic level.
Yeah,
But-
people use Markov models of the transition state. I don't know if I don't think it would matter. I think that this is empirical. This is if you build a model which has C and then C1, C2, C3, C4, C5, and 1, and you run a simulation across it just by discrete state Markov chain stuff, you find that if you perturb this C, let's say C1 to C2, or I've added catch here, by the way. This thing crosses binding and gating. This histogram only pertains to gating. But if you perturb something, let's say after tilt, you do 1, 2, 3, you're going to get a phi value of 0.58. It's just an empirical thing with states. Whether you can get there with Cramer's or these other fancy ways of doing the transition state, I really don't know. That's beyond my
Yeah,
ability.
what I was intuiting, and it might be wrong, is that you might be able to do it with fewer states. But I think the way that you're mapping onto the structure in discrete areas argues against that to some extent.
Yes, I would agree. It's not 100%. I'm really taking. I could show you the raw data, and it's not perfectly as clean as these boxes that I'm showing you, but it's not exactly like this. Every now and then there's a green event down in here. We find a green event, or we can find a red event over here. But this is just generally the picture that I'm just summarizing what we see. You can go to the original papers to see where everything falls out. But I'm trying to sort of give you our view of the whole thing. I don't think Cramer's makes a difference. I'll have to think about that. But I think you're right that the fact that they map onto structure so clearly. And I think this is actually quite a useful result. The things that are more than 15 angstroms away don't talk to each other mostly. So that's I think an important result that allows you to turn these different phi values into specific mapping onto structure.
Do you think that's general for proteins?
Yes. My view is, I don't know, there's got to be long range transfer information in a conformational change. My view is it's going to be through the backbone. We don't have any data for that. I don't know if that's true in general, or I don't know enough about conformational change or protein folding, things like that. But somehow the information has to be transmitted through the whole system.
Yeah.
We see very little of that taking place through the side chains. And I think that's why the backbone of these ACHBP and ACH, who only have 30% homology in terms of sequence, behave the same way. I think it's the backbone that gives you that global isomerization of the protein. But I don't know that. That's beyond what our data has to say. My guess would be if we use proline mutations, we might start seeing something different. But
certainly in voltage gated channels, some of the packing between some of the helices is definitely important. So that side chain packing.
For what? For long range transfer of energy?
Or so voltage sensor to pore coupling.
Okay. So you mutate those side chains, you get voltage sensor changes. You can change the voltage sensor.
Yeah.
Okay. All right. Well, we haven't found those in this protein, so there may be a few. We thought we found some at the protein at the extracellular transmembrane domain interface. There are some mutations in here which seem to have a high phi value, but that's a little bit dicey because of something called the Hammond effect that we didn't take into account. So, but let me finish up. I'm getting near the end here. So I want to try to get this over with. So here we go. Here's the zipper. It's the idea is there's a sequence of linear free energy relationships like that cube I showed you, but it's a It's a 6-dimensional hypercube, so you can't draw it. It's not useful to draw it as a state model. But the idea is that the agonist shows up, lowers the transition state for the catch, which lowers the transition state for hold, for lowers twist, lowers tilt, and all of a sudden you get to rip and pop, and then the channel opens. So you have a sequential lowering of the transition state as in a zipper. Just like I showed you for those two, catch and hold are the first 2 teeth of the zipper, but there are 6 teeth of the zipper. And similarly, if you make a mutation that brings down the stability of the open state, because of that microscopic reversibility, you lower the transition states in the reverse order just the same, including across the binding gating divide, and catch happens. So if you have a constitutively open channel, you automatically, whatever that catch rearrangement is caused by making the channel open by a mutation far at the gate. So you can make a mutation right at the gate that stabilizes the gate in the open state, and it'll propagate back and it'll make catch happen. So all of these events are linked together in a giant chain of linear free energy relationships that I call a zipper. That's my model for how this works. So here it is. Agonist shows up. And I'm showing each transition state lower, being lowered by the previous event. Twist, tilt, rip, and then pop. I'll show that one more time. You can look at the structure now. Catch, hold. Twist turns out to be the hardest one. Twist. You can actually get some idea of the heights of these barriers if you really look into it. So twisting turns out to be the most energetically unfavorable event. Now, there's the last thing I want to say is that if you notice the beginning and end of this, catch and pop both involve changes in water. So the AC, if I was from the planet Pluto and I would look at the ACH receptor, I'd say it's a molecular device that effectively transfers 5 water molecules across a 5 nanometer low dielectric gap in about 5 microseconds. It doesn't move the same water molecules. That's why I use effectively. These water molecules come from the extracellular and these come from the intracellular compartments, but it's a water transfer device. So it goes from wet, dry to dry, wet, closed, open. Closed is wet, dry, and open is dry, wet. Now, I don't know if this is stupid or profound. I got a feeling it's stupid, but it's just something that I've noticed, and I'm just going to point this out because I'm among friends that something to do with water going on there. And it's about the same amount of water. It's 5 to 10 molecules in each one. So with that, I'm going to end and show you the summary. Now that's the beginning, the outline. I think you understand what I'm talking about now. You have these unusual results that you can see the efficiency and efficiency classes, the barcode idea, and then catch was the from the binding rates, and you combine those two, you get this linear free energy relationship that changes with agonist structure. The 5 values give you a conformational wave forward and backwards, which was mapped onto structure because of that Newton cycle analysis, and that's what gives me the zipper. So that's the summary slide, and I hope you understand this better than you did when I started. So that's it. I'm going to just give some thank yous. These are the 4 people who did most of the efficiency work. The wave was a huge project that started with Claudio and Ming Zhou, and the people who worked on efficiency also worked on the wave. Basically, everybody worked on the wave for 20 years in my lab. The MD simulations were done by Susri Tripathi and Wenjun Zhang and Sri Rupa Chakraborty, who is now at Boston College or Boston University, I think. Did some work on desensitization and other receptors. I just want to mention the results. So the consultants, John Richard and Rob Colson, turned me on to linear free energy relationships. So I talked with them not only about 5 value analysis, but about that tethering of the catch and hold. That was from Rob Colson's discussion. And my son, I put on this list, Eric Auerbach, because one day at Thanksgiving, I told him I didn't know what an energy, we knew that the energy ratio was constant. I didn't know what it meant. And he's an engineer. he's a thermodynamics engineer who works on wastewater treatment plants. He deals with gigajoules, but he just said, well, an energy, that's called an efficiency. So that he turned me on to efficiency. And these are some of the other people. I've had fabulous technical support. I've had great funding from NSF, got me started, and NIH kept me going, except they don't want to fund me anymore. So the story may be coming to an end. So anyhow, I'll just say thank you. Okay.
Thanks, Tony. That was really great. I had one little question on the water.
Yeah.
Do you know what the values of the streaming potentials are that suggest how many waters are coming per ion?
Oh, no, I don't know. If you
Somebody did it. It was a long time back, and I don't remember either.
Yeah, I don't remember either. I also don't remember if people have done contraction of the binding site with osmotic. That's another way to test for contraction of the binding site, because you are squeezing out waters when you.
Yeah, and I don't remember any ACH receptor work on that. Maybe
Oh,
somebody
I
else
don't, I
does.
don't, with other receptors, but there are experiments that could be done to test that. But I
Yeah,
think
it was done in gramicide and in water. I mean, in potassium channels mostly.
Yeah, I think MD is going to be the way we get those
Yeah.
the numbers now. I think that was before.
But it'd be really nice to have an experimental test to go
Yeah.
along with it.
Yeah.
John Danny do some water streaming with the NACH receptor?
What? I
And
wrote.
John Danny do some streaming water?
Oh yeah, Roger, maybe. I think that's worth looking into. I think you're right.
Yeah, I remember.
Yeah, I don't know what the answers are. I just made up. I just sort of guessed at 5. It could be 10. It could be. I don't know what it is. So,
Thanks for the invite, Tony.
but does this have any cachet? This water thing? I mean, I think it's stupid. I think it's probably just a silly observation, but it just seems to me. Does this happen in any other channels? Does the voltage channels? Is there a change in the disposition of water at S4?
I think there was a trip channel. We did a journal club in our lab one time. Murali Prakriya was the PI on it, and they made a big deal about water in the pore.
Yeah, I think most of the voltage gated channel stuff has been water in the pore, not water in the voltage sensor. But since the charges in the voltage sensor seem to be exposed to solvent, you could probably get at it that way, especially with some of those S4 mutants that allow more permeation through the S4 pore.
Yeah, I don't know. I just noticed this, and I don't know what to make of it. So I just thought I'd put it out there, and just in case somebody had something to say about it, because I don't know if it's even worth bringing up.
It'd be interesting to see if osmotic pressure is actually an outside energy source.
Yeah, I mean, it turns out it's faster than you could diffuse the water. If you go that distance by just water diffusion, it takes longer than 5 microseconds. So if you actually wanted to move water across 5 nanometers, it would be much slower. Of course, with the low dielectric, you couldn't do it, or it would take a lot longer. But even with a high dielectric, it takes longer to go 5 nanometers than a few microseconds.
But squeezing the space and changing the the liquid hydrogen bond network could change the energy a fair amount.
But actually, Rick, if we're doing the osmotic experiment, you have these two that would offset each other. One becomes dry and one becomes wet. So you may not see anything. You know what I mean?
Right. In equilibrium, it may go away.
Yeah.
Right.
Yeah.
It's not really water flux.
It's not water flux.
Right.
No,
so you
but
wouldn't
it's
expect a streaming potential.
Yeah, right.
It is right.
But it would still be osmotic pressure sensitive though, for accessibility's sake.
Yes, right.
So any other questions about any of this junk that I have here?
There's a question in the chat. Does membrane constitution affect efficiency?
The problem, I don't know. I have no idea. I don't know. It might.
It'll be interesting to look at.
it would be very interesting to find things far away from the binding site that affected efficiency. I think that would be illuminate something that we don't have. It would give you a new thing of information, although we don't have any examples, so I can't tell you whether it happens or not. But
It pretty much has to be there though, right? Somehow or another.
yeah, somewhere. But
Yeah.
I'd say it might be in the backbone as opposed to the side chains.
Yeah.
But now, what about this barcode idea? Is that going to be hold water for other receptors? I mean, it's so clear that the classes of efficiency in ACH receptor, it seems to me like discovering the line spectrum of a sodium ion or something like that. That it's really it's a remarkable separation of those efficiencies for 20 different agonists. You would have expected them to be just spread all over the place, and they really align tightly. So,
Yeah, I would wonder how much of that correlates, as you've kind of alluded to, is the volume of the binding site. And you would think that maybe if you found mutations away from the binding site that changed efficiency, they may not change the barcode
yeah.
in some way.
Yeah. Yes, that would be very interesting. Far away, the binding site still goes to its target structures,
Yeah.
but the springs that couple that with the gate at the bottom
Yeah. Right.
are a bit effective. So you're right. That would be a key finding, that the barcode would stay the same, but the efficiency would drop.
And you may get a correlate with your phi values with the ones that are further away from open or something. I'm not sure. It depends
I
on
think
what
phi-
exactly is going on with that.
I think phi is probing L0. It's not probing efficiency.
Yeah.
So what you're probing in there is side chains that you're changing the stability of the side chain in C versus O, and you're asking whether that transition from stable to unstable or whatever it is happens relative to the transition state.
So the barcode changes may give you a different wave map.
Absolutely. I think it's testing something very different.
Yeah.
That these things are testing L0 and that's testing efficiency.
But doesn't the barcode sort of represent that there are that the binding site can only occupy certain specific states?
Structures.
So structures, right? I mean, that's all it's really saying, is that the compression, if it goes with compression, it just sort of says the binding site can be in state or structure A, B, or C. And then the question becomes, what determines those structures, and are they modulatable by anything far away?
But the efficiency goes beyond the binding site structure, because you have to couple that with the rest of the conformational change of the protein. So there are springs attached to the binding site that either push the energy or pull the energy to make it out. It's interesting that the binding site contracts and the entire extracellular domain contracts. They both undergo a contraction between closed to open. So it's like the binding site pulls, and somehow that pulls on the rest of it. So it could be the binding site pulls the same, but you have broken one of the springs that couples that to the next movement in the chain. So if you did a structure, you could see the discrete four structures. I agree with you, Andy, that's our hypothesis, that each of these bars represent a discrete target structure. And if you make a mutation near the binding site, you might change that structure. But if you make a mutation far away from the binding site, as Rick was saying, that you would leave those structures the same, but you would see a different efficiency. So
you could generalize that idea to distribution of structures, right? Not a different structure, but a different distribution.
You mean you're talking about
of the binding site?
Variance. You like the variance idea, you mean?
Yeah.
Yeah, sure. We don't know if it's the first, second, third, or fourth.
Yeah, no, I mean that's a very Wyman influenced point of view.
Yeah. But if it was related to
I don't think Wyman discussed efficiency, though. Someone
but about distribution changes was a pretty big deal for him.
Leon Islas told me that efficiency was in that original Wyman paper, and I went back, and that paper is horrendous. I couldn't even read it. But I don't think that this idea of efficiency, I think, is new in terms of the ratio of those two energies being what efficiency is. I don't think that the hemoglobin guys never did this. The BK guys
Yeah.
never did this. I don't think.
I agree with that. I don't think that's in the original Wyman stuff.
Yeah.
Yeah, and I don't think it's in the book either.
It's so amazing because this stuff has been around it's been
Yeah.
hiding in plain sight.
Another thing though about the barcode idea, Tony, isn't it correct that for when you're talking about a different receptor, it would have a different barcode, which is kind of the idea of a barcode, right? Like each product has its own unique barcode that identifies it uniquely, right?
Well, I'll tell you that the ACA at the gamma site, this black bar moves from 51 to 56%. It moves to the right of the green one in the gamma subunit. I think it's site specific. Each binding site has it.
Oh, really? The subunits are different. That's pretty cool.
Yeah.
So even within the same receptor, that is interesting.
Yeah, you change the other side of that binding site. You know, we haven't done it at all with the same detail as this. I would love to do that, but I don't know if I'm going to get there. But to see how this thing changed at the alpha gamma site would be very interesting.
But it is a different protein. I mean, the different subunits are different proteins, so it's not crazy to think that their barcodes would be different, right?
Well, yes, but I also think that if we make a mutation, some of these mutations that change, we've only looked at a few agonists, but they're going to shift the barcode to the right. They change the barcodes by making mutation at the binding site.
But again, that's a different protein when you've made a mutation. So
yeah, but
the energetics are
again,
different, and
the energies don't propagate very far. So yeah, it's a different protein, but more than 15 angstroms away, that guy doesn't know what's going on. I mean, you don't know what, when you have two side chains 15 angstroms away, you have no idea what's going on at the other side chain. It's the energy changes are not influenced over that distance. So there's a lot of local stuff going on too. So when you say a different protein, I tend to think of, that's why I don't like that KNF thing, because lots of local things are going on. I think it's not just a subunit behaving as a subunit.
But I mean, the efficiency depends on the efficacy, which depends on the gating, right? And so you could have a mutation far from the binding site that does affect the gating, right? So that's going to influence all this stuff.
Yeah, I haven't found any though. We haven't looked very hard, but so far, I mean, there's somebody I'm working with in Oxford who wants to do congenital myasthenic mutants that are far from the binding site to see if the reduction in efficiency is a common feature of congenital myasthenia, because we found that one that dropped it from 51 to 42, but that was at the binding site. But those mutations are spread throughout the protein, so maybe that's going to show something. I kind of doubt it, but that's a possibility. But I think there's a lot to be done here. But I think efficiency is a very general thing, and I really want to encourage everybody who works on GABA receptors or any receptor or voltage gated channels or anything, just to try to make this efficiency plot. This efficiency plot is extremely informative.
So just along those lines, we found a mutation in the interfacial linker region there that changes diazepam efficiency.
Efficiency.
Yeah.
Yeah, it changes it by about 3%. It increases it whenever you, and you can see the current, and like there's more current there, and you calculate the efficiency, and it's more efficient. Right there on the M23 linker.
Well, that's far from the binding site. So there you go. I mean, yeah, which one is it? Is it not that proline in there?
No, it's the valine right in the middle. It may be an isoleucine in some subunits. I think it is in nicotinic, but yeah, it's yeah. I was just wondering, because I was wondering if the changes in like the different classes, the efficiency classes that you have in that barcode, are different, like poor coupling pathways.
Yes. 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 I mean, that's, let me just say that in this plot here, these guys here that are outside this coupling range are in that linker. That's what led us to the idea there's a long range change with that linker. But yes, if I go back to all the way back to this mutant page, maybe I don't need to go back there actually. But your question, are things that change efficiency in the coupling pathway. And that's my hypothesis is yes, these guys here. So
Yeah.
these guys here, 198 and 93 don't change efficiency. I don't think those guys are involved in getting energy out of the binding site. I think 190A is involved, and that's in a pathway that touches 145. We're walking down this pathway to see how the efficiency changes with mutations. There is a pathway that Steve Sine defined that's of exit of energy out of the pathway. And W149A also is involved in getting energy to the pathway. So yes, I think when you change the efficiency and G153, we don't know how these are. We want to make double mutations to see if these things are interacting with each other. If you make this drop in efficiency and this drop in efficiency, what do you get? Do you get the same drop in efficiency? So I think yes, that if you changed an efficiency, we'll change the energy transfer pathway out of the, and the coupling will give you some insight into the mechanism of that. But yeah, NIH didn't like that aim, so I'm dropping it from the next grant submission.
But I think all this together, nicely fits in with Cindy's question about whether drugs can alter the efficiency classes, which I think is a really cool idea, and it's something that may not happen so much in an ACH receptor because it doesn't have all the complex pharmacology that GABA receptors have.
Right.
I'd love to see that actually happen. I bet it does, Cindy. I bet you're right.
Well, I think you could think of a drug like a mutation. They're the same thing.
Right.
It's just a structural perturbation. So if it could happen with a mutation, it could happen with a drug. This has to bind there.
I think that's mostly L0 though. I don't think that's eta. Eta is what the efficiency is. I think most of the time when you add a drug, you're going to be changing L0. That's my idea. Just like, because drugs are like
a local thing.
What?
Affinities are a local thing.
Yeah.
Right.
Yeah. So you have to change KD and KDO in order to change affinity. So if you're far away, if you change efficiency, that means you have sent a message a mile away, across a light year away. You've sent a message back to the binding site saying, don't go to that binding pocket, go to a different binding pocket. And it's hard for me to actually imagine that. I don't know. I've never found that. So my guess is when you add drugs, you're mostly changing locally, that local, you're changing E0 or
Yeah,
L0.
but I guess if you have a binding site that's within 15 angstroms of your agonist binding site, it could do something.
Oh, sure, if it's that close.
Yeah.
Yeah, I was talking about long range. But yeah, if it's that close, anything can happen that close. Yeah, right, exactly. So, but are there drugs that bind near the GABA receptor binding pocket?
Benzodiazepines do.
No, they have their own binding pocket. No, they have their own binding site, right?
Yes, they have their own, but they're close.
But do they affect the one across the way?
That is a somewhat contested question. But, yeah.
I bet you not. My bet would be no. That's too far away. ACH receptors are completely independent. If you knock out a binding site and you measure the affinity, you knock out the other bite, you measure the affinity, you put two together, you get the same. It's in that same paper of the cyclic model paper. They're completely independent. And it's like, and they're independent and roughly equivalent for the adult type receptors. And if you do it with the fetal type receptors, they're completely independent. So whatever you get with one.
How about in the homomeric alpha 9? Are they completely independent?
Claudio, I don't know that at all.
I think they're completely independent.
Okay.
Yeah.
With benzoyl
from our data.
Yeah, that's what that's what I'm.
I mean, it's not even 15 angstroms, it's 12 angstroms is what it is. So it's like anything 12 angstroms away in this protein, nobody knows what's going on. It could be it could be in Afghanistan. You don't know what's going on there. So,
My bet is that it's longer in some types of proteins, that they've evolved in a way that selects for longer range interactions. But pure speculation.
Yeah, I mean, with things like benzos, there's some things that just don't make sense with a pure change to L0 only.
Mhm.
Are there other physiological or any physiological modulators of GABA receptors?
GABA receptor.
Neurosteroids.
Uh, and yeah,
I think there's some like endogenous like stuff that acts at the benzodiazepine site too I think there's multiple.
PBI,
Yeah.
diazepam
Yeah.
binding inhibitor.
Probably lipids too, right? There are lipid effects.
In the
Cholesterol and so on.
extracellular domain, probably there are lipid effects in the
Yeah,
transmembrane
membrane
domain,
yeah.
a little bit.
but do those change enough to be a modulatory signal?
Not that I know of in the GABA receptor, but
Yeah.
the neurosteroids are definitely endogenous.
Yeah, definitely. Yeah.
But, I just want to try to convince people to do this analysis. You have the data. If you do a dose response curve, you can get the efficiency. And if you get the efficiencies for enough data, you can make this plot. Okay, each one of those points is a dose response curve. It's a lot of data, but now you have these high throughput systems that you can do, scan 100 compounds on a fast. Does anybody have one of those machines? That you can do these high throughut screens.
Just drug companies.
Anybody have a friend at a drug company? You can go through that and just make this plot. There's nothing esoteric about this plot. It's Max and EC50. It comes from the most primitive measurements you could make about a drug. 1925, they could have made this measurement.
But high throughput's expensive.
Yeah. Well, anyhow.
I have to run.
Okay.
Hey, Cindy, thanks for coming.
I'm glad you guys waited around for 2 hours. That was a long way to go.
Oh, it was
This
great.
was really amazing.
I loved it.
Okay.
So let's.
I'm going to be late.
Bye, Cindy.
Okay. Bye, Cindy.
Bye, Cindy.
So
Let's do it again in a sort of less formal way if you want. I'd love to do that.
well, we could gather a group of interested parties.
Yeah.
Not necessarily at a department seminar, but maybe I want to have a group of people talk about this idea of the gating currents are in the vertical lines. And what could possibly, I don't know what the energy is coming in. You could get there from structure. It's charge times. What's the difference in the charge between the closed and open of BK? I mean,
About 1 per subunit. It's around 4 charges between open and closed
all right.
across the whole field.
So you could get you don't have a signal from that though. Is that what you're relating to the gating current? My view is the gating current could be a different signal than that signal coming into the, I talked to Pancho about, is this the Paquito? And he says, well, maybe not. I don't know.
Yeah, I don't know. The Paquito kind of died after a while.
Yeah, so I don't know, but there could be another signal in there that's not.
Yeah. Well, the gating currents are happening, maybe 70% before opening, but there's a component that happens along with the same time course as opening in BK.
So I would say the Paquito, the analogy of the Paquito is hold. That if you go to this map,
maybe
this map, hold is the gating currents. The move, just like the collapse of the binding pocket is what's happening in hold. That's when the contraction takes place.
It's not that fast though. I mean, a lot of gating charges moving a lot slower than that.
Who cares? This could be as slow as you want. The slower, the better.
Okay, yeah. You're not defining this as a flip state.
Just raise this big barrier here.
Yeah.
So, that's just how long. That's just the energy of that next step in the process. So this is the gating current would be hold, and catch would be the deposition of energy coming in. That would be the analogy. But maybe we could organize something like that. I mean, Claudio has ideas about that. Claudio, you still there?
Yes, and I disagree with you.
Yeah, you
But,
disagree. Right.
I may be wrong too.
Disagree about what part?
No, I mean, we often talk about voltage gated channels, and we disagree in that I think Tony thinks that the equivalent of the unliganded ligand gated ion channel is a voltage dependent ion channel at 0 transmembrane potential.
And voltage is an inverse agonist.
And I think that, I mean, the whole treatment could be different. That one can think of the S4 transmembrane segments as a particle that has two binding sites. So it can bind in the up position, it can bind in the down position, and that I don't even remember too much. It's been a long time.
No, but those aren't incompatible.
I mean, at some time, I think when we were talking individually, Zooming the two of us alone, we were having some heated discussion. And I don't remember now why I got mad. And I think I thought he was wrong, and he didn't like what I said. So then we hung up. But
well, the idea of voltage being an inverse agonist is something that Joe Patlak was really into. Is that what the voltage sensor does is
keep the channel
holds the channel closed.
Exactly.
Hyperpolarization is an inverse agonist. And
right.
It's an agonist.
Yeah. But then different voltage gated channels do their action either above or below 0. And so, it's not general that way.
Sure.
But the idea of efficiency is not very useful with voltage-gated channels because there's voltage is voltage. It's not like you have a slew of agonists and get a barcode. I mean, you're just changing the voltage.
Right. Yeah.
You're not going to have the families. It's the families that make efficiency interesting.
But what's kind of cool in BK is that you can bias the efficacy with calcium because you're changing the energetics of open and closed with calcium, and then you can let the voltage work at high calcium versus low calcium. And so it's sort of a neat experiment that you could do that way.
So that's the difference between those two blue bars. So you're saying
Maybe.
you can change one of the blue bars. You change one of the lengths of the blue bars.
Yeah. So applying this in detail to BK, having the two energetically basically equivalent activation pathways could be pretty interesting, I think. And you could do high calcium, low voltage, and low calcium, high voltage. You get the same PO, and see what's changed with some of these calculations and with gating currents and things like that.
Well, that's another seminar. After you go ahead and get the data, Rick, and then you can give us seminar. We'll talk about it then.
Right.
So I'm still curious at how do you think about these interfacial residues and where they fit into this pathway? The ones that are, at least by the phi value, are suggested to maybe move early on.
Yeah, well, the problem that I always get tricked in those phi value analysis because of something called the Hammond shift, and that the slope of the line can change with the equilibrium constant, and the ones that were high phi values at the interface, which we identified, those are these guys down. Whoops, these guys, they're not that far away. So yeah, these guys here that we found that were coupled and high phi, they were loss of function mutations. So usually when you make a mutation, you increase the gating equilibrium constant, but those ones were lost. And when you lose the equilibrium constant, then everything tends to go to a slope of 1. So that you change the shape of the transition state. You move the transition state around so that you make the transition state late, so that everybody looks like the phi of 1, that they look open at the transition state. So the transition state is malleable. This is one of Claudio's things. So you can move the transition state left and right. And what you're measuring is the character of the residue at the transition state. So if the transition state is moved to the right to very late, then everybody's going to have a phi of 1. So it's only when your transition state is roughly in the same position can you make that map and compare them. And some of those were very large loss of function. So I'm not sure. I got tricked. I've been tricked on that several times. I got tricked on that with voltage too. So I'm not 100% sure that those are genuinely high phi in comparison with the ones that are in the rest of the protein. But I don't. What's your question, Marcel? About what do you want to know about those, or what?
Yeah, that was just it. I was wondering how you thought about those, because we've been trying to interpret some mutations that we have down there, and the one potential interpretation from them was if they're moving early in these sort of spontaneously active receptors, that we might not really observe effects there. And
what?
That some of the effects that we see in, say, mutants or channels with lower spontaneous activity, we don't see in other mutants with higher spontaneous activity. And so one of the potential interpretations was maybe that something was going on in an earlier step that we'd sort of biased the receptors past already by boosting the PO. I don't know if that is going to hold up yet.
I don't know. I don't know what to say about that. I'd have to look and see what the data was like, because I really can't. I don't really know. But my thoughts on that used to be that there was a critical event down there that started the whole thing going, and now I'm not sure I'd put a lot of money on that. But because of that Hammond effect shift that I didn't take into account. So
Does the Hammond effect cause a nonlinear FER?
Yeah.
If you could see?
Yeah.
That is exactly what it is.
Okay.
Yeah, that's what
The
it
loss
is.
of linearity of a linear free energy relation.
And you know what? There's also an anti-Hammond effect. If you make mutations at the gate, you get a different curvature. It curves up instead of flattening over, which is a Hammond. It actually curves up, and that happens with mutations specifically at the gate. So, but most of these are linear. I think most of the mutations that we made to make this map are
The
straight.
linear part.
Yeah.
They're mostly linear, and I think that's
over a fairly wide range too, right? Like your earlier ones were. I mean, I was really impressed by that. They were linear over 4 log units or something.
Yeah, over a very wide range, and I think that's because the transition state is roughly in the middle.
Mm-hmm.
So that you're not moving it around. But some of these at the very end cause this anti-Hammond effect. Those guys are right at the zeros, or where you get the anti-Hammond effect. So you're moving the transition state very late by making a mutation there. But that's very complicated because it involves the side of the saddle that you're moving up one side of the saddle. Yeah. And it's like, I can't figure it out. That's sort of too hard for me. So
just to come back.
Go ahead.
Just to come back to the distance dependence of things. So this interfacial mutation we found that affected benzos, it's probably not that far from the site, maybe roughly 15 angstroms or so. And it's right below the pocket is the linker we found it in. And some new data we have now that's not published yet, in the other subunits, there's no effect. So it's literally only in the subunit whose linker sits right below the benzo site will you see this effect. So maybe there is some, something to the distance.
Maybe there is something. Yeah. Well, Marcel, you should measure efficiency. You have the data. One dose response curve. All you need is one dose response curve. Every dose response curve gives you an efficiency.
Yeah, but we'd have to figure out the PO max for every mutant. So.
Yes, you have to figure it out for every mutant.
Yeah, you can't do it macroscopically.
Yeah, but yeah, it would be cool to know. Absolutely.
Why can't you do it macroscopically?
Because you don't know the max PO.
Sure you do.
Number of channels
Let's
in the
go- Why not? Why don't you know the max PO?
Because you don't know the number of channels.
Yeah, but you normalize it. If I go, let me go all the way back there. It's going to take a second here to get back there. But in our wholesale currents, I'll go back to this one here. In our wholesale currents, we just normalized to this response. We didn't know the number of channels. So we put on 300 micromolar choline, get a response, then do a dose response curve of epibadidine, TMA, and we do another one of this.
Do you do that all in the same cell?
We do it at 16 cells. This is an ion flux machine. I'm not exactly sure. It does a whole bunch of cells together.
But are the different agonists applied to the same cell?
Yeah, right.
No,
Good.
but no, we measure the star for every cell. We do a calibration of what 300 micromolar is and normalize everything to 300 micromolar.
Okay, so
Yeah.
okay, every single cell is tested with ACH and some
Yes.
other agonist.
Yes.
Yes,
yes,
yes, yes.
Yeah. Yeah.
So we can definitely, do that. And Gustav Ock's done that a lot with so GABA doesn't open with PO1, but he puts on combinations of various things. And the idea is hopefully that's PO1. And it's maybe not a horrible assumption, although once you start making mutations, you always wonder.
It doesn't
We-
have
we
to be
know
a
that
PO
this
of
is-
one as long as you know what the max PO, I mean, the PO of one ligand is, right, at
Well,
saturation.
Yeah, but the problem is, once again, once you make mutations, you don't know.
It is also true that being a whole cell type of experiment, stuff happens when you run electrophysiology on a whole cell. You have run down, run up, stuff happens.
Come on, Tony. I just don't want to hear you proselytizing about doing whole cell experiments. It just doesn't fit the phenotype. It's
I mean,
Well, this is just a straight up wholesale experiment.
sure, but it's a coarser measurement than if you can do singles.
yeah.
Oh, singles are much better, of course.
Sure.
But we knew this max was PO. It was actually not 1. It's 0.93 because we measured that at single. So
Right.
we measured this, and we knew everything was based on that. So you'd have to do a singles to know what the
Sure.
PO max is with GABA receptors. But
You
that's
also need-
we did. That's in our paper with.
And on every mutant.
But you also need to understand, Tony, that this is probably working very well in a muscle nicotinic receptor because desensitization, desensitization doesn't affect too much the peak currents because it's relatively slow. In other channels or other mutants, desensitization gets in the way because it shortens the peak. So
Hey, it works in muscarinic receptors. I think it'll shorten the peak, but you'll get the relative efficiency of.
I don't know.
the
We start
ligand.
making assumptions, we can get very far from truth. But,
Somebody should try it, but this is what you should do: is you should measure the binding constants biochemically. Do a biochemical assay, measure KDC and KDO. Get yourself a bucket of KDC, make sure it stays KDC, and get yourself a bucket of KDO, which is the same as desensitized.
Sure.
And you just measure those.
That's
two.
simple.
You do
And the full channel in the lipid environment that's actually gating while you're doing it.
you don't want a gating.
Well, then
Prevent it from gating. You stop it from gating. You kill it, so it doesn't gate. You put down in the membrane. You do.
okay, so you assume that the only thing you've done is kill gating.
Yeah.
Okay.
You kill gating. You just change L0. You make L0 very small, so that you don't get any energy from the ligand. Enough energy to make it open. The binding sites stay low affinity, and then you go to high affinity. You make L0 very large or whatever to make it so that you measure the high affinity binding. Desensitize is the same affinity as O. So you just measure those two biochemically and you calculate efficiency. You don't need to do
I think you can only do that in a receptor you already understand pretty well.
I would do it. I would try it and I'll bet you it's going to work.
Yeah.
No one's
Because
doing it.
I don't even think killing gating necessarily does what you think it's doing. It could kill it in the high affinity state, or it could kill it in the low affinity state.
I don't mean kill gating. I mean make L0 extremely small. Add mutations that drop it down to 10 to the minus 12th. So when you get energy from the ligand, it still doesn't open.
Yeah. Okay. Yeah, so it's a limiting slope kind of
I'm
argument.
not talking about a scissors or a knife or anything.
Yeah,
like that.
yeah.
I'm talking about make L0 very small.
Yeah.
So I think ultimately that may be a good way to go, but we'll see. I mean, the problem is nobody else is doing this. So it's like, I'm trying to get someone else at least trying to do it. And I think if you close your eyes and did this, it would work on GABA receptors, for example. It works.
But I also think that macroscopic currents aren't always easier to do. Sometimes it's easier to do the singles and get the data.
These were singles. These GABA A were Trevor
Yeah.
Smart singles, and he did this horrendous analysis based on clusters. I give him a lot of credit. It was a terrible way. But these other guys are macroscopic. No, I think glycine is singles too. That's from Civilati. But these two NMDA stuff came from, that was macroscopic, and so was muscarinic was macroscopic.
Well, Marcel, didn't we calculated it a little bit in our paper, right? And we got like 37% for GABA.
Yeah.
Yeah, we did it a little bit.
Yeah, you got the same number. And also, it's the same number for the intercept here, that this is 10 to the minus third or something like that, which is what GABA is, right? It is a very high spontaneously open probability, or constitutively open, right? Unligand, I think Gustav Fox measured when you put on picrotoxin, you can actually see the current drop from without any ligand, from an unliganded state.
On a wild type?
I think so.
Yeah.
It might be higher than a voltage gated channel, but it's not big.
It's still pretty low. I think it's like 10 to the 7th or minus 7 or something like that.
Because we come 10 to the minus 3, 10 to the minus 4 with this plot. And I thought that was in agreement with, these guys are 10 to the minus 6, 10 to the minus 7.
I don't really remember off the top of my head right now. Marcel, maybe you probably remember more.
I actually don't either. I want to say it's closer to 10 to the minus 7, but it might be 10 to the minus 6 or 5. I mean, that might not be that far off of what it's been estimated.
I vaguely remember reading a Gustav paper where he actually put picrotoxin on a zero, and saw a drop in the current.
It depends on the subunit composition in
that's
GABA
true.
receptors.
Yeah.
Well, that's another thing, is that low probabilities are easier to measure with singles.
There was definitely a paper like that for an alpha beta. I don't remember the numbers, but an alpha beta gamma combination. But they did this crazy overexpression thing in oocytes to be able to see it, and it was kind of wonky to read the methods. But yeah, it might be there, but it's not high. Like in a normal cell, you don't see it. If you put on picrotoxin with alpha beta gamma, you don't see anything.
I guess you see it if you use the beta 3 subunit.
That might be the case.
Yeah. I think because we're in alpha 1 beta 2, and that's it. And I think the beta 3 subunit makes it.
The beta 3 that makes the whole difference.
Yeah.
Okay, I think we're burned out.
Hey, fantastic. That was really fun. I definitely appreciate you doing it. And thanks, Claudio and Andy, for coming along. And it was wonderful.
Yeah, thank you all. It's good seeing you all. I'm not going to biophysics, though, so I won't see you in person.
You'd miss me anyway. So
okay.
Let's talk again,
Bye,
Tony. Let's definitely do it again.
Okay.
This was awesome. Thank
Okay.
you.
All right. Thank you.
Bye.
See you, everybody.
Great to see you all.